Next speaker is Adam Sobel. He's visiting us from Columbia University, where he's a professor in applied physics and math. Adam has a PhD from MIT, and he did a postdoc in Seattle, and he's been at Columbia for, since last century. He's written a number of different papers on lots of different topics, all, I think, informing his view on the impacts of global warming on weather and climate. And he, in addition to scientific papers, he's also written a book called Hurricane Sandy, Our Changing Climate, Extreme Weather, Past and Future, available on Amazon. Sorry, Storm Surge, Hurricane Sandy, Our Changing Climate, Extreme Weather, Past and Future. So check it out. He's also going to be speaking on Friday, giving the keynote speech in our public session. Title is, he doesn't know yet. No, come.
But
yeah.
I gave you a title.
We don't remember it, but he's going to be talking about disasters and climate change, the global and the local. So please give your attention to Adam, and also please join us on Friday for the public event that will happen on the main campus. More information on that later. Adam.
Thanks, Amy. Thanks, Ben. Thanks, guys, for organizing this and having me here. More on hurricanes, and Chris and Tom's talks in the morning warmed things up very well. A lot of things I won't have to repeat. A lot of people's names up here, because I'm going to summarize a few different pieces of work, a couple of which I wasn't involved in. I'll give you an outline in a second. But this is about so Tom talked about detection and attribution. Chris talked about attribution. And this is not exactly about that. This is more about what we think should happen or should be happening now and in the future, and why, and some things we understand and some things we don't understand. So this is my outline. I'm going to talk not about every aspect of hurricanes, but intensity, which is how strong they get, frequency, which is how many there are, and both of those topics I'm going to be talking about some work from our own group at Columbia. And then at the end, I'm going to talk about a couple more important recent results from the climate literature by people who are in this room, including Amy, who just introduced me, that I wasn't involved in. And they're not on the program, I think, either because they're polite and don't want to put themselves in the program here, or because there weren't really work that was done about hurricanes. But I think it's incredibly important for the present and future of what we understand about hurricane risks. So I'm going to mention it because that's why. So first of all, intensity. How strong do hurricanes get? What do we know about it now? So some background. We think they should get stronger. Tom said that. There's already been about a degree of warning, so have they been getting stronger already? We've got the detection and attribution. And so Tom studies the latest, but the literature that they're summarizing, some studies say yes, they've already gotten stronger. Others say no. What I'm going to be focused on here is should they have gotten stronger yet? And the theoretical background, we think hurricanes should get stronger, not only because models say they should, but because we have a theory for it. It's developed by Kerry Emanuel with contributions from others in later years. And there's a thing called the potential intensity, the hurricane potential intensity, which is a thing that if you know the climate at a given place, you know the large-scale conditions, this theory tells you what's the strongest hurricane you should have. And there's been a lot of argument over this, but it's held up pretty well. I'm not going to explain it in detail. I'll show a formula once, I think. But we think this is a good guide. So in other words, we have a reason beyond just the models for thinking that hurricanes should get stronger. But if you look at the trends in this thing called potential intensity, which you can compute from data, the trends aren't so clear. I won't show the details, but that's background. And so we're going to look in the models and try to say what they predict and try to understand that. And that'll give us some guidance as what might be happening. So that's the first thing. So here's a map of how this quantity called potential intensity, which you can think of it, so it's measured here in meters per second unit of wind speed. So it's what's the strongest wind speed you could have for a hurricane in this climate, and how do we expect it to change in the so-called RCP 8.5 scenario, which is a strong warming scenario, by the end of this century compared to the end of the last century. So red means the hurricanes should get stronger, and you see red almost everywhere. Significant, these are pretty big numbers, except you see blue here and here, but there's no hurricanes there anyways, it doesn't matter. This doesn't tell you whether you'll have one or not, it just tells you if you had one, how strong it would get. So we expect, this is the expectation, by the end of the century, and if you don't like RCP 8.5 or you don't like the end of the century, it doesn't matter, you can change the numbers. The point is, this is the direction things should be going. As it warms, we should get stronger hurricanes. And yeah. So, but if you look at what the models say about the recent history, the models actually say it shouldn't have increased that much yet. What happened? The background of this is we were going to write a review paper about this, and this was an area where I thought we sort of understood it. And so I thought we're going to look in the models, and they're going to say they should be getting stronger, and the reason we don't see it yet is because of natural variability. But actually, that's not true. When you look at the models, they don't say they should have gotten much stronger yet. This is potential intensity over time in the CMIP5 models, are our best climate models that have been in an IPCC report that's already published, the new ones being worked on now. But the black is the historical potential intensity, and it's basically flat over the whole late 19th, early and 20th century, a couple dips due to volcanoes. It only starts trending up in the end of the century. That's the black. Now, the red is what you get if you, instead of forcing it with so this is a historical simulation. You force it with everything. Greenhouse gases, aerosols from humans, natural aerosols from volcanoes. That's what causes these dips, as I said. But the red is what you get if you force only with greenhouse gases. So no aerosols. Then you get don't worry where 0 is, doesn't matter. But you get only an increase over time if you force with greenhouse gases. So the warming from greenhouse gases should make stronger hurricanes, but that's not what the models say should have happened historically, and the reason is because of aerosols. So this more bluish, greenish thing, forgive me, I have poor color vision, whatever color that is what you get if you force only with aerosols, so volcanic and human aerosols. Oh yeah, that might help, thanks. So yeah, this one, is aerosols only. So that, if you only had aerosols, you'd be getting weaker hurricanes or weaker potential intensity. And if you add them together, you get about this. So the contributions from greenhouse gas warming and aerosol the aerosols are little particles in the, little bits of dust or liquid that block the sun and cool the ocean, and that suppresses hurricanes. So this increase is about equal to this decrease, and if you add them, you get the black. Don't worry about this one that sort of shows that in more detail. But if you add them, you get the black. So the aerosol and the greenhouse gas are about canceling. And this is kind of interesting because the greenhouse gas forcing is actually stronger than the aerosol forcing by maybe double. I mean, that's why we have global warming, right? If the aerosols were cooling as much as the greenhouse gases were warming, we wouldn't have warming, but we do. But when it comes to hurricanes, they cancel. So it turns out that we measure radiative forcing in watts per meter squared. That's the sort of how we measure how strongly some radiative agent is changing the climate. So the forcing from greenhouse gases is about double, but it turns out that a watt per meter squared of aerosol forcing is about twice as effective in how it affects potential intensity than a watt of greenhouse gas warming is. So even though the climate warms, the greenhouse gases win in that sense, but when it comes to hurricane intensity, they don't, until maybe recent years. So that's what we want to understand here in this first part of the talk. We want to understand this factor 2. And this has turned out when we dug into this and started to understand it that there have been a literature for a few years now showing that the same thing is true if you look at precipitation. A watt of aerosol is about twice as effective as a watt of greenhouse gases in changing global precipitation. Here's some references. And it's going to turn out that the reasons in hurricane intensity are approximately the same reasons, but it's still worth going over it, and some of the details are different. So here's the theory of potential intensity. So this is an equation. I won't show many equations, but this is the square of the potential intensity. So the maximum wind speed you could have in a hurricane, theoretically, is this V pot. And so the square of that is proportional to a bunch of stuff. Oh, my math fonts got messed up. Ugh, I should have thought of that. I don't suppose we have the PDF. Well, it doesn't really matter. You can see this, okay? So the bottom line is, okay, the potential intensity depends on the disequilibrium between the sea surface and the atmosphere. So they'd be in equilibrium, the ocean and the atmosphere would be in equilibrium if the atmosphere had the same temperature as the ocean surface and it was 100% relative humidity. But it's not, it's a little cooler and drier, and that disequilibrium is what drives hurricanes, and potential intensity measures that. Now that same disequilibrium also is directly a big part of what controls the surface flux, the evaporation of water into the atmosphere. And in the global mean, the evaporation has to equal the precipitation. So that's why precipitation and potential intensity behaves sort of similarly. And so you can use, so it means if you can understand what controls the latent heat flux, you can to some degree understand what's controlling hurricane potential intensity. And what this shows, this is where so this should really be an enthalpy disequilibrium term here, but what's been done is we've assumed energy balance at the ocean surface. So these are the radiative fluxes at the ocean surface in the short wave and the long wave, and as well as the ocean heat transport. And this is the mean surface wind speed. So basically, if you know the radiation and ocean heat transport that's warming the ocean surface, then the evaporation has to balance that, and that's similar to potential intensity. So if you understand energy balance at the sea surface, you can explain potential intensity, and that's what we're going to do here in the models. So we're going to look at the single forcing CMIP 5 run. So these are simulations where instead of putting all the forcings, you only put one at a time. Greenhouse gases, but no aerosols, or vice versa, et cetera. So these are some details. I think I'll skip it. We're just looking at the tropics instead of the globe, which is different from how you have to treat precipitation. But I don't think I need to spend time on that. So here's the basic thing again. So this is now a different version of like the plot that I showed. This is the potential intensity showing that if you have aerosols that go up, if you have aerosols, it goes down. If you have potential intensity, it goes up, and those are about equal, and the sum gives you this, plus the volcanoes gives you this wiggly thing. This is if you look at sea surface temperature instead of potential intensity, and then you can see that the greenhouse gas warming is much stronger than the aerosol cooling. So the fact that the difference between the red and the blue is lopsided here but symmetric here is the problem we're interested in. This is this is time. Okay, and this is changes in potential intensity or SST. This is taking, and these are means of a lot of different climate models. You can look at the single models, and some of them are different, but a lot of them are kind of similar enough that we think taking the average is meaningful. And now I'm going to take individual points from the time series and scatter plot these two quantities against each other, just so you can see that. So this is sea surface temperature change here versus potential intensity change here. This is the aerosols, and this is the greenhouse gases. So you can see that the slope is very different. Okay, that's the thing that's another way of visualizing what we're interested in here. So you change the sea surface temperature a little bit, and if you're changing it due to greenhouse gases, potential intensity doesn't go up that much. If you're changing it due to aerosols, it changes by more. And the difference is that greenhouse gases change the radiative balance. It's what they do to radiation at the surface that hurricanes care about, whereas the climate as a whole is affected by what happens at the top of the atmosphere. And the difference is that the greenhouse gases act in the infrared, the long wave part of the spectrum, and the aerosols are affecting the short wave, what comes from the sun, visible mostly. And that turns out to be what makes the difference. I think I will, well, okay, yeah. No, I'll skip this. I just want to get to the one main result here. This is a result, so what you can think about is, we think about it in terms of feedbacks and forcing. So like if you think about the aerosol forcing, you put a little aerosol, it cools the surface first because the short wave, this visible radiation basically goes right through the atmosphere. It isn't absorbed very much. So when you put some aerosol, the first thing that happens is you cool the surface. The atmosphere doesn't feel it until it feels that the surface is cooled, and then the whole atmosphere cools. But that changes the temperature and water vapor in the atmosphere, which is a feedback back to the surface. And there's a way of untangling that called radiative kernels. It's actually invented here by Brian Soden, as far as I know. And we use that to deconvolve it. So what's shown here is our attempt to do that. So this is the change in sea surface temperature versus the change in either the latent heat flux, which is our proxy for potential intensity, the surface evaporation, or, so think of this as hurricane intensity on this axis if you're looking at the circles, sorry, the diamonds rather. And the circles are the feedback, so they're the part of that we can explain by the temperature and moisture changes in the atmosphere. Okay, so, and the blue is aerosols, the red is greenhouse gases. The black you could ignore, it's when you put them all together in the historical, but that's actually harder to understand. And the different symbols are from different individual models, and the filled in things are the multi-model mean. So this result is kind of complicated. This is like the, sort of for the experts, but how you want to interpret this is the diamond is how much change, how much for this amount of aerosol cooling of the sea surface, how much potential weakening of hurricanes you get. And this little bit is the amount that's due to the feedbacks from the atmosphere. And it's mostly not due to that. So that means it's the direct forcing by aerosols. Whereas with the greenhouse gases, the difference is less. So the interpretation, my math fonts are totally botched here. So you don't try to read this sentence. That's what happens when you don't look at how your PowerPoint looks at the other machine. Anyway, how we want to interpret this is the difference is because the aerosol, most of the contributions from the direct radiative forcing to the surface, and not as much due to the feedback. And the long wave, the greenhouse gas forcing, the direct is less important. How I think of this physically is that the short wave goes straight through and warms up the sea surface, and it's only through that the atmosphere warms. So it has to go through the equilibrium. You have to increase the air-sea disequilibrium for the whole system to respond, and it's that disequilibrium that drives the hurricanes. Whereas in the long wave, the greenhouse gases warm the atmosphere and the ocean together, basically. So the disequilibrium is less, and it affects the hurricanes less. So that's kind of a technical result, but it's just to say that we do understand, to some degree now, why the aerosols are more effective. And that's what I said. The direct force component is much more. So I'm going to get to frequency in a second. I just want to say the implication of this is that the models say maybe we shouldn't have seen that much intensity increase yet until recent years. But going forward, but you can see in the latter part of the time series I showed here that the greenhouse gases are starting to win lately. You're seeing PI trend up. And going into the future, greenhouse gases are increasing fast, whereas aerosols aren't. They've already gone down in the US and Europe due to the Clean Air Act and similar. And they're probably going to be regulated in Asia, too, because people are choking on air pollution in Beijing and Delhi and such. So the fact that we've had this cancellation up to now is just good luck, and it's not going to continue. So the intensity increases we've seen in the past are not a good guide to what we're going to see in future global warming. OK, now a bit about frequency. So frequency we know much less. As Chris said, I think, and Tom both said, we don't know that much about the number of hurricanes. A few years ago, the models had been starting to say, we had a new generation of high-resolution models, and the models had been starting to say there should be fewer hurricanes as the climate warms globally. But nobody really knew why they were saying that. They were saying it, and we knew the models weren't far from perfect. They were just better than what we had before. But we started to believe it and tried to rationalize it. I mean, we wrote some papers ourselves trying to to rationalize it. But recently, some credible models, it's still a minority, but they're good models, predict that there should be more hurricanes and not fewer. And we have no theory. Unlike with potential with intensity, there's about 90 plus or minus 10 hurricanes, tropical cyclones, I should say, per year on Earth, tropical storm intensity. Why that number and not double or half or triple, or we don't know. We're not even disagreeing. We're not even fighting over it. There's like nobody even has it's not like we have different theories and we're debating it. We don't even have it. Nobody has any good ideas. So that makes it kind of hard for us to explain the changes. If we know that we start to trust the models, but then the models change their answers. So that's what we're interested in here. I'm going to show some results from our particular model, which are not going to answer it, but they're just going to give you a more idea of the problem. And maybe I'll suggest how we might think about it. So Chris showed a slide from our model. It's a sort of statistical dynamical hybrid. It's basically a sort of Monte Carlo method that generates synthetic hurricanes cheaply, but it knows about the climate they're in. So you have to model genesis, the formation of storms, then the track, then the intensity. The intensity is probably the most interesting part, but I'm not going to talk about it because I'm interested in frequency here, so I'm interested in genesis. So genesis is how do you form a storm? What we do is we use a so-called empirical genesis index. There's a long history of using these for other things, and we're using it here to decide how many hurricanes there should be in our model. So this is the probability of genesis, and it's a function, an exponential function of a bunch of environmental variables. So there's a vorticity that makes them not happen on the equator. Don't worry if you don't know what that means. There's a humidity variable, very important here. There's a thermodynamic variable. This is a relative sea surface temperature, but we actually use potential intensity, which I just explained briefly what that is, and wind shear. So a bunch of things. You have to tell this model what the climate is at each point in space and time. And then we have a formula that says a hurricane is this likely to form. And then we randomly generate them with that probability. That's what turns out to matter. So let's just focus on that. Here's a slide from our model. Chris already showed it. These are the observed hurricane tracks over some number of years, color-coded by intensity. This is our model. It has some biases. There's too many here and not quite enough in the Atlantic and so forth. Let's not worry about that for the moment. This is the main result I wanted to get to. So this is what happens in our model if you project hurricanes going forward in the future, just the number, just not worrying about the intensity. Actually, what's most interesting about our model, what it's most useful for is thinking about intensity. But But this is what it does for frequency. So this is the black is the historical number of cyclones on the Earth. This is reaching at least tropical storm strength. I keep saying hurricane, but some of these are weaker than hurricane strength. But anyway, so it fluctuates up and down, doesn't really change that much. And our model says that it's tuned to get the right answer back here, but in the future it's not tuned. So in the future it gets either an increase or a decrease. And what we've done here, I should say, we have to get the climate from somewhere. So to do the future, we get the climate from global climate models that we think they're the best we have for predicting the climate, but they're not very good at hurricanes. So we get the climate from them, and we tell our model, this is the climate. Now you use your formula and decide how many hurricanes there are. And that's the formula I just showed you very quickly. And it gets either an increase or a decrease, and we did 6 models. So you might think what I'm showing you here is that some models predict this and some models predict that, depending which climate you get. That is not true, actually. This is, these are the different models in different colors. Don't matter. It doesn't matter what these acronyms are. It's 6 good, actually 5, sorry, good climate models. And the difference here is not which model you use, because the same color goes both directions. We did 2 sets of calculations with these models, doing one thing differently in our model, and that's which variable we use to represent humidity. As Chris said, hurricanes need a humid atmosphere, but there's different ways of measuring humidity. And the difference here is whether you use the relative humidity or the so-called saturation deficit. The relative humidity is how much water vapor you have in the atmosphere divided by the maximum you could have, the saturation value. The saturation deficit is the difference of those 2 numbers. And if you plot them both in today's climate with the right color scales, you can't tell the difference. But in the future, they change very differently because the relative humidity doesn't change much, but the saturation value does. So the relative humidity doesn't change, but it's the same fraction of a bigger number, and the saturation deficit increases because of that. So if you use saturation deficit, the number of hurricanes goes down. If you use relative humidity, the number goes up. The relative humidity in that case doesn't change, but the potential intensity increase causes it to go up. And we do not know which of these answers is right. I mean, this answer, more models favor this one, but some good models favor this one. And our flaky model is what it is. I mean, it's semi-empirical and whatever. But it's the state of the literature. The reason I didn't talk about the rest of our model is that the Genesis index is all that really matters for this purpose. You didn't even really need to run the model. You could just look at the Genesis index. But the Genesis indices are just empirical fits. They're just, we know something about the historical and geographical variability of hurricanes and how it's related to climate, and we're just putting that into a formula. It's not really a theory. But it's not exactly that. This is a technical point. Our model can cause some storms to die so soon that we throw them out, and then so it's not just the Genesis index, but that's basically it. So that's our model, but it's a real scientific uncertainty. This is just, I don't think I'll really explain these figures. This is just to say these are figures from 2 pretty recent papers with pretty good models. I think this one is probably about the state of the art, actually, that predict increases in the number of hurricanes any way you look at it, which is just, and whereas we used to think there was a decrease, and here's a figure from the IPCC showing in one particular basin that a decrease was expected. And this was done before these studies came out. So we'll see what CMIP6 says. So we just don't know, I think, whether there should be an increase or a decrease. What you do about that information, my view, if you actually have to, how to deal with that scientific uncertainty if you actually have to make decisions about hurricane risk, like if you have to price it in the reinsurance world, is a value judgment. And science can't tell you. My view is that we should treat this uncertainty like we treat other forms of uncertainty. And if we can't rule out the idea that hurricane activity may increase in the future, the hurricane frequency may increase in the future, then we have to treat that as a possibility. And then that, in some sense, means the risk is going up because there's a risk that the risk is going up, if you will. This is just to say if we look at individual basins, so that was all global. This is the Indian Ocean, the Western North Pacific, the Atlantic is here. You don't see as bimodal a split. In other words, here there's no scenario that gives anything in between the increase and the decrease. In the individual basins, it's a little less dramatic, but there's still a very large spread and an uncertain sign of the change for the same reason. Do I have a few minutes left? How might I do, Amy? Okay, great, perfect. So 2 more points from literature, and this is stuff from some of it done here, some of it done at Columbia, by Amy, who's here, Mark Kane is in the audience, my colleague Richard Seeger at Lamont, and their students and postdocs. These are two new relatively recent things that one can say about the Atlantic specifically, so where we are living now. That it's not my work. I'm going to be very brief about it. I'm not the right person to present it, but I just think these results are so important that they should be mentioned here. So first, Tom talked about the multi-decadal variability in the Atlantic. So this is an old paper showing how this is major hurricanes as a function of time, and it's up, and then it goes down in the 70s and 80s, and then it comes back, and we've sort of been somewhere in here for a few years. And so this has been attributed to the thermohaline circulation. People know it's natural variability, so it goes up, it'll come down again. Who knows what climate change is doing. But the new evidence, there's a lot of new evidence coming out of here especially, and Mark's been involved in it. This is by Katinka Belomo's paper, one of Amy's students, which suggests pretty convincingly to me that at least the recent Atlantic multi-decadal variability is not just due to the thermohaline circulation, but is actually, to a large extent, forced radiatively by greenhouse gases and aerosols. In other words, we've seen that the greenhouse gases warm the climate, aerosols cool it in a way that affects hurricanes strongly. That was particularly strong over the Atlantic in the 70s and 80s before the Clean Air Act cleaned up the aerosols. There's a lot of sulfate aerosol coming off North America, going over the Atlantic and cooling it, and that's suppressed sea surface temperature and hurricanes here. And what these plots show is that this is observed versus some model simulations with a lot of models that show that you can, to some degree, simulate this if you have radiative forcing, if you put in the anthropogenic radiative forcings. So this dip here is to some extent forced by aerosols. Sorry, this one, forced by aerosols. And then this increases when the aerosols go away and the greenhouse gases take over. And if you don't have those forcings, you don't get it. This is just one result. They have a bunch of papers about this and a lot of different results. But it's just to say the implication there is that even though the thermohaline circulation is there and it varies, maybe there's historically is an Atlantic multi-decadal oscillation, but the recent variability may actually be human force. And if that's true, that's another piece of evidence that this low period we had in hurricanes, this is hurricanes here, is less likely to come back than we might have thought if it was natural variability, because this aerosol cooling is not coming back over the Atlantic. So we're more likely to be up here in the future than down here if you believe this. So I don't think the hurricane community has absorbed this result yet, but it's pretty important. And the second one, which is even newer, this is from a paper led by Richard Seeger, but Mark's a co-author on it, says that, and this is something that goes back to Amy's thesis at Columbia many years ago, models could all be wrong about future sea surface temperature trends in the Pacific. So all the models say that if you look into the future, this is trends in sea surface temperature in the Pacific in two observational data. So how much has it changed from the 50s to the present in observation? So it's warming everywhere except it's cooling on average, despite in an El Nino event, this would be warm. In a La Nina event, it's cool. The trend is more La Nina-like over the last half century or 3/4 of a century, even though there have been a few big El Nino events. But all the models say it should warm more on the equator. So the models are doing the opposite of what the observations have shown. And the case, I think, has become stronger. So Amy said this 25 years ago, but the change has become, the evidence has become much stronger. I won't try to explain their compelling physical argument for why the models are wrong about this. But just suffice to say that in an El Nino event now, my point here is in an El Nino event, this is the Pacific, but when there's an El Nino event in the Pacific now, it suppresses hurricanes in the Atlantic. When there's a La Nina event now, when it looks like this, you get more hurricanes in the Atlantic. So if they're right, then the models are predicting a climate which is going to lead you to underestimate Atlantic hurricane activity, and it's going to be worse than the models say for the Atlantic specifically. It'd be good news for the Pacific, but bad news for the Atlantic. So I don't think the hurricane community has absorbed this at all. So I'm just saying it here. So those are the things I wanted to say. So our results that I talked about, expected tropical cyclone intensity increases have so far probably been muted by aerosol cooling, which per watt per meter squared is about twice as effective as greenhouse gas warming in changing potential intensity. But the implication there is that that's not going to help us that much in the future because greenhouse gases keep going up fast while aerosols, if anything, are going down. But no clarity on tropical cyclone frequency, even in the sign. And I think this is a really urgent problem for our field. We've gotten close to nowhere on it in many years, and I think we have to change something about how we're thinking about this. But if I knew how, I would have done it, and I would tell you. But it's a really scientific problem. And then I just mentioned this from the recent literature. The AMO, I think there's compelling evidence, although the oceanographers are still fighting over it, but I think there's compelling evidence that the AMO, the Atlantic multidecadal oscillation, is in large part radiatively forced, which implies that the slow Atlantic hurricane period in the 70s and 80s is not as likely to come back as we might have thought. And if the recent results on the Pacific are right, that's another thing that looks bad for the Atlantic, because it means that the models have been projecting a future in which Atlantic hurricanes are probably being suppressed by an El Nino-like mean state much more than they should be. Okay, that's all I have. Thank you.
Okay, we have time for a couple questions. Okay, Nick Shea here.
So Emmanuel's theory on maximum potential intensity really relies on that coefficient between the enthalpy as well as the drag coefficient. Mm-hmm. Could you give us some sort of an idea of what that looks like from your model?
In our model, I cannot tell you what the number we use is. All we do is, what we do right now is we compute the potential intensity from Kerry's code, and actually the way the code calculates it, that coefficient, it's in the efficiency factor. There's an alternative way of doing it with the capes. But I'm going to claim that for the results I'm showing here, it doesn't really matter, because we just hold it. The only thing that would change this in any major way is if you believe those numbers would change with climate. In other words, if you pick a number and you hold it the same, then you get this. So, in other words, how you deal with those coefficients will change the absolute value, yes, very much so, the ratio of those coefficients. But if you leave that, we're leaving that ratio constant. I can't quote you what the numbers are. But what would be a big problem for these calculations is if you had a good scientific argument why that ratio itself should change with time. Then we'd need to rethink the whole thing. But as long as that doesn't happen, you'll change the absolute value if you change that ratio, but you won't change the trends.
Okay, looks like we have a hand going up. Brian Mapes.
Hi, Adam. Just besides frequency and intensity, there's the question, and longitude distribution, Pacific versus Atlantic, there's latitude distribution.
Yeah.
That Jim Cosson likes, and it's sort of maybe it's a proxy for landfall, because there's, the fates of them depend on what latitudes. Do you think that's theoretically grounded and extrapolable and, clarifying in any way?
I don't know. If you compute potential intensity from the climate models, you do see a bit of a poleward expansion of the regions where it's high. In our model, for what it's worth, which is taking the climate models as correct and just downscaling it, we don't get a large poleward shift, not nearly as large as in the observations, if memory serves. And we also do not get a slowdown in translation speed either, which suggests that if the argument, and I didn't talk about how we do tracks, but it's Kerry Emanuel's track model, which is a beta and advection. It basically takes the winds and steers the storms around with those from the model. So if the argument for the slowdown in translation speed is that, you didn't ask this, but it's related. If the argument for the slowdown in translation speed is because the tropical circulation is slowing down, then we're taking that from the model. So it's not enough, apparently, to give us anything that looks like what Jim sees in the observations, which is not to say that we're right, but it's just to say that the explanation can't be that simple somehow. But the poleward shift, we don't get a large one. I don't know why.
Okay, one more question here. Tom?
On the equatorial Pacific SST trends and so forth, we've been looking some at, say, sea level pressure trends and all too. And one thing we find is this really strong period of really strong trade winds around the time of the hiatus. And those things don't seem to be modeled. We don't capture them as internal variability or as forced response in any climate model. So it's almost like maybe models are underestimating some form of natural variability in terms of what can happen to the trades. So do you have any comment on that? Does that resonate at all with any what
I
other
think Mark
people are
should
finding?
answer that, but I'll just say that that is not the explanation in their paper.
I'm gonna jump in because this is gonna get, I'm sure we'll continue this discussion, but I think it's a good question about how, weather models are representing the internal variability, and we have different points of view on that topic in this room, so we'll continue that. Thanks, Tom.